Good morning, all. Welcome to the another session of advanced concrete design. As decided, today we'll be going for the pile cap design. So just respond me whether the slide is moving or not in the chat box. And I hope that I'm audible to you. Okay, thank you. So let's carry on straight away without any preamble because this would be the concluding session, I guess, regarding the last topic of the ongoing unit, that is design of foundations. I received a couple of requests regarding the material sharing. I will try my best to provide you all the materials, so don't worry about on that part. However, all the online sessions will be shared with you so that you can utilize the documents during the examination. So friends, pile foundation and pile cap foundation, it's a unique foundation that is a part of the deep foundation, as we all know, right? And on the right hand side you can see a couple of options of providing piles, and necessarily a column like structure, that is the element which is connected at the top by means of a rigid pad. Now this rigid pad is interesting component, and that is what is called pile cap. So we are focused not on the pile design, please understand. We are interested in designing the pile cap itself, that is the pad component, because that is a primary component which holds all the piles intact and in place. Now there may be a question that what if we don't provide this component, it will not suffice the primary function of distribution of the forces. So pile cap is unavoidable component of the deep foundation and a must-have component in the pile foundation itself. So piles are commonly used in a group of more than one. That doesn't mean that it is not used in a single pile. However, it is a very rare phenomenon when it is required to be used as a single pile. So when a group of a pile used, they are connected through a common slab known as cap. So the pile cap is a structural member used to connect group of piles, resist the pile reactions, and transfer the external load to the group. So we should understand what is the primary function of the pile cap is to transfer the superimposed load, that is the applied external load from the superstructure, as well as it is subjected to the reactions by the piles. Because by principle, if we understand pile foundation, it transfers the force to the adequate strong bottom, right? So when the strong bottom is encountered, the pile is inserted and transfer the forces. So there will be a reaction, definitely, and because of this reaction, the upward force that is applied to the cap itself. So you should understand that cap is subjected to dual set of forces. One is downward and second is upward. And therefore, the depth of the pile cap is very important component of the design, and on which we should always focus, especially in case of the shear resisting capacity of the concrete that you are using. So it is to be understood that normal concrete, this is from the practical point of view, normal concrete mix is not suitable for any sort of pile cap. At least you should practice with M25 and above, and with a heavy reinforcement. So you are going to see some of the interesting images also in upcoming slides, which shows the cage-like structure of the pile cap. So sometimes pile caps are provided below the ground level also. In that case, topsoil has to be considered as loading itself. So depending upon the actual condition, you should take in to the consideration of the forces. So that's a pictorial view, illustrative view of the pile cap itself. The combination over here is shown with a simple illustration. When the adequate strata is not available, you are bound to use piles, but they are connected at top. And here the footing, let us say, individual footing is supported on a set of piles or group of piles. So they transfer the forces to the ground by means of the cap itself. So here is the reinforcement detail. As you can see from this pictorial view, the pile cap is provided with reinforcement in all directions. As I said earlier, it is what is the need of this? Because it's not like an ordinary slab, or I would say it's not a slab itself. It's a kind of a block. It's a concrete block which is subjected to upward and downward forces. So therefore, it is necessary that each let us say or centimeter of the pile cap is subjected to the tremendous shear force. So only concrete may not be sufficing the requirement of the resistance to these forces, and that's why steel is required in all directions, along the depth, across the depth, vertical, horizontal, and sometimes additional steel is provided around the pile itself to reduce the stress concentration. That you will see probably in the next slides. So this is a combination of or the shape of the pile cap, where the shape of the pile cap depends upon the number of piles in a group. So as you can see here, it begins with two piles where one column is to be supported if it is heavily loaded. Then it may go up to any numbers. See, there is no limit of numbers of piles in a group. But the only thing is how you design the pile cap to resist these forces. And it is not also required that unnecessarily you increase the area of the pile cap. So there are some design aspects on which you should focus while designing the pile cap itself. These are some pictorial view of the pile cap design. As you can see in the first image, the concreting is being done in the formwork of the pile cap, and there are three piles provided, and above that, when you complete the pile cap, it looks something like this. After that, you provide some reinforcement also, and on the last side you can see four piles are connected through a pile cap, and a reinforcement for the pile cap is also visible in the right hand side figure. Here another set of pile cap reinforcement you can see easily and more clearly, that you can see there is a mesh like structure. So right now you can see only the bottom steel is being provided, but gradually you have to replicate this steel into the reverse direction also, right? So before we move further, please add your names in the chat box for the attendance as usual. Okay, so this is, I would call, complete pile cap. You can see the amount of the reinforcement that is provided. Tremendous reinforcement, very closely placed reinforcement is provided in all directions, like top, bottom, vertical and horizontal. So it's a box like structure, pad like structure. And on the right hand side, you can see there are some additional steel is being provided just to reduce. However, the number of pile is only one. Here you can see or the column is only one, but in the bottom there may be at least three piles. Because of the shape itself, we can understand that how many number of piles are minimum provided. So here it is provided in the a kind of box like structure. This is another image. You will find plenty of images online, and I insist that you should also inquire about at your end. Here, four piles are provided, and pile cap you can see heavily reinforced. Right. So, needless to add that you don't have any other option than using the ready mix concrete because the restrictions of the congested reinforcement always in the pile cap. So the question comes is how pile cap works. So they ideally work on two principles. First principle is the strut and time model, where you can see here in some of the figures, like it is assumed that the bottom part of the pile cap works under tension, and throughout the thickness of the pile, the shear force or ideally compressive force exists in the pile cap. Right. So you have to decide, like it's up to an engineer who is designing the pile cap. He or she must understand which principle or which theory is to be adopted. So pile cap follows the load transfer pattern as per the strut and tie model, especially when the number of piles are limited or ideally up to four in a group. So strut and tie model is ideally suitable to be adopted when there are limited number of piles. But let us say you have 10 piles or 12 piles in a pile cap. So at that moment, you should not ideally go for a certain time model because it doesn't suffice the minimum requirement of the certain time model. So minimum requirement of certain time model is your distribution of the shear forces should follow 45-degree load transfer pattern. But it is not satisfied when you have more numbers of piles. So it is ideal for two or let us say up to four. Right. This is just for your information I'm sharing with you. So there are certain design aspects on which we should focus. However, these are the theory points. So at your convenience, you should go through this when I share this with you. But here, as per the IS 2911 code, right? There is a code which is dedicated for pile foundation, basically not for the pile cap design, but somewhere and somehow they have shared some details regarding pile cap also. Like it is desired that you assume that the forces are transferred at 45-degree from the top to or top of the cap up to the mid depth of the pile cap from the base of the column or pedestal. The reaction from piles may also be taken into the distributed at 45-degree, right, at the edge from the edge of the pile. So in short, when you are following this principle, you are indirectly following the strut and tie model. On this basis, the maximum bending moment and shear force should be calculated at the critical section. So where will be the critical section? Definitely when you create one line, imaginary line, like here in this case, when you create this imaginary line, and this would become critical section for you. Similarly, just below the base, where there is no compression is assumed. So in that case, the entire behavior of this portion will look like a beam, right? Or ideally deep beam. So there will be a fear of the flexure also sometimes if the spacing is too large between the given piles itself. So there is a complex behavior definitely of the pile cap, especially in case of more number of piles. So ideal condition of the analysis will be you utilize some simulation packages. There are plenty of packages available which helps you to design pile cap. But at least before you jump into the actual design, my advice is to have a hands-on experience of calculating pile calculation or pile cap design by hand itself, manual itself. So in that line, let's go ahead and let's see what are the design assumptions provided in the pile cap design. Pile cap is perfectly rigid. That is the first assumption. Second is the pile heads are hinged to the pile cap, and hence no bending moment is transferred to the pile from the pile cap. Now, this is very important assumption. You would have an argument that, sir, we cast everything together and how we can assume that it's not rigid as a connection, right? As an element, it is rigid. That means it doesn't allow any sort of flexural or elastic properties within the pedestal itself. But as far as the connection between the piles and the pile cap is concerned, we assume that the primary function of a pile cap is to hold the piles in position. That's it, nothing beyond that. Otherwise, what happens is you have to unnecessarily design the piles themselves for the bending itself. It becomes like a cantilever in that case, rigid cantilever. That means fixed at one end and free at other end. So once you introduce bending inside the piles itself, I'm talking about pile itself. So the diameter will unnecessarily get increased, and the behavior will not be predictable, because once it goes into the flexure, it starts behaving like a slender column also, because the length of the pile is tremendous always, right? And that is why it is called deep foundation. So here we have to understand, we have to assume that piles are just getting connected and placed in shape and in place by means of pile caps itself. Since the piles are, however, in actual practice or in reality, there is some effect of rigidity at the pile cap and pile itself, and which introduce some sort of negative bending moments at the connections. But these connections are very well taken care by the steel or the amount of steel that you provide in pile caps. You have already seen that the pile caps are provided with a tremendous amount of steel. So none of the section will suffer from the lack of the amount of steel or reinforcement. So in that case, by default, the flexural part is taken care by the pile cap. So ideally, it is assumed like this. Especially this assumption, that means second assumption, becomes very important when you are designing the pile itself, which right now not the case. Right now we are focusing on pile caps itself. Since the piles are short and elastic columns, the deformation and stress distribution are planar. This is also assumption, right? But when you come into the actual practice and when you take the slenderness ratio, it may happen that the pile are no more a short member. They don't act as a short member. So they act as a slender member. So in that case, again, you have to calculate the stress distribution at every joint or every node or every refined model that you are creating in the simulation, and that is only possible with the software, right? So as far as the manual calculations are there, I would say these are the assumptions for manual design of the pile cap itself. So there are some design parameters or design aspects that we have to focus, and first is the shape of the pile cap. Now, I would say shape of the pile cap depends on the number of piles in a group available. As you can see here, if you have limited number of piles in a group, you can definitely design them in whatever form you want. The only thing is you have to maintain the spacing of the piles and the placement of the main columns on which, under which we are providing the pile cap. So here you can see some of the options. There are plenty of options available for the shapes. You can even go for a circular shape for, let us say, 4 piles, 5 piles. There's nothing wrong in that. The only thing is you have to take care about the surrounding area which is available to you, and it should not be disturbing the other setup of the, let us say, neighboring columns also. So the shape of the pile dimensions on the depends on the spacing of the piles and how you get the spacing. There is a small equation here where spacing factor is provided, that is the center to center spacing per pile diameter. That shape factor or spacing factor has to be utilized, and where HP is the diameter of a pile. Right. So like that, here you can see in all four cases, there is some specific value of the center to center distance of the piles is given, like in this first case 1.5 times d, where d is the, of course, the diameter of the pipe. So this is a minimum spacing that you have to maintain, right? And that will basically decide the overall dimension. See, we are not interested to provide any additional or extra or unnecessary area in a pile cap, right? That is not at all needed. That will not help also. Rather, it will create problems. Why it will create problems? Like, it will invite unnecessary flexural movement, because we assume that from the center of the pile cap is like a rigid body. But if you extend this part unnecessarily, it will start behaving as a cantilever, right? And that will invite unnecessary upward bending moment because of the upward soil pressure also, because ultimately pile cap is always in touch with the ground and experiencing some thrust from the ground also. However, the downward force is usually so high that this upward thrust is usually neglected. But in case of unnecessarily large area of a pile cap, it will create some problem in the flexion. So please have a practice that do not provide area which is not more than required, right? So likewise, it's up to your choice in which shape you want to provide the pile cap itself. Now, this is regarding the theoretical aspects of the depth, how you decide the depth of the pile cap, which is very necessary to discuss. Like, there are some combinations of the provisions of the IS code, let us say 456 and 2911. But here, as far as the minimum thickness is concerned, the minimum value should not be less than 300 mm. That we should understand. At any section, any part of the pile cap, whether it is at the corner or at the edges or in the center, minimum thickness should be 300 mm. So it is but natural that when you have a thickness of 300 mm, you are bound to provide two side reinforcement also. While generally speaking, the pile cap thickness should not be less than 500 mm, which may be reduced to 300 mm again, as we say. So in my opinion, when you are designing a pile cap, please maintain your minimum thickness up to 500 mm. Right. Now, this will not harm to the overall behavior, because ultimately it's going to be a block-like element. So there is no fear of bending or flexure. So try to maintain 500 mm as the thickness, and you can maintain a slope, a very fine slope, which is maintained from 500 to 300. So you can create a slope like structure also, but that will unnecessarily increase the formwork exercise. So ideally, pile cap should be designed as per the block element, where all the dimensions are equal. Right? So there are other provisions also, like for pile caps to be rigid, the pile cap has to be quite deep with 600 mm as the minimum depth. So there are three criteria we can see and suggested by different code provisions. Even the British standards or the American standards suggest that if the behavior is expected to be the rigid one, you should go for 600 mm. So you take a wise decision while you are deciding the depth of the pile cap if the load is not significant. Sometimes the loading governs the thickness, or the bending even governs the thickness if the pile spacing is large. But otherwise, you have to follow the standard values. So in our view, standard value will be minimum 500 mm. Right. So as a guideline, the formula given the reinforcement by Reynolds. This is a very good book. I would like to suggest to all of you. It is available online also as a ebook. You can search on design of the reinforced concrete structures by Reynolds. So it is full of the formula, and it is a very useful book for all the structural engineers. Even I used to use this book when I was practicing. So in my initial days. So you can also take help of this book. If it is possible, I'll also share this with you, and you can have it during your exam also and during your practice. So according to the Reynolds theory, uh, there are some equations available. You can see here, like pile cap depth is expressed as 2 times HP plus 100 mm for pile diameter more than or equal to 550 mm, where HP is given as the pile spacing and pile diameter. So you can obtain this once you go through the original formula in the text. You will get to know the better equation. For our case, right now, what we are going to discuss as a pile cap design, we are just going to refer to the two piles in a group. So where it will not be effectively utilized, but otherwise, in a real-time condition, you can definitely use this book for reference. So this is a pictorial view, like for the design parameters regarding the thickness of the pile. This type of the equations and this type of formula are given in the Reynolds book, which will be helpful to you. However, we have here some standard values of the pile thickness, pile cap thickness, depending upon the pile diameter. You will notice that there is no direct relation given on the, or importance given on the uh, pile load, or the load on the pile cap and the thickness at this moment. So why this is not given as an important parameter? Because primarily your shape of the pile cap will decide the behavior of the pile cap itself. As I said earlier, if it is limited in numbers, you can adopt the theory of the Stratton-Tie model, and that's why the spacing will be accordingly decided based on the diameter of the piles, and overall dimension of the pile cap will also get decided according to the diameter of pile and spacing. Therefore, you just only need to take care about the tensile force which exists in the bottom of the pile cap. Why it is important? Because sometimes if the tensile stresses are not very well taken, there is a fear of bursting force. That means the upward force which is exerted by the piles, and if the pile cap is not designed accordingly by provided with the necessary reinforcements in the bottom, there is a chance of failure of the bottom of the pile cap. And that is why you should always take care about tension force which develops in the Stratton-Tie model type of the pile cap. So otherwise, you can straight away adopt this data, like pile diameter and pile cap depth. So for 300 it is 700 mm, and so on and so forth. You can see here, if the pile diameter is beyond 600 mm, the depth of the pad or pile cap should be around 1800 to up to 2000 mm also. That gradually depends upon the diameter of the pile, and you can interpolate these values also. These all are like formula and tables available in the Reynolds book also, and any reference, standard reference, you will find this kind of data. Now, there is one more important aspect regarding the steel in the pile cap. I have already specified that pile cap requires steel in all directions. So you will see some images on this side that it's just like a box of the steel, right? So when you create a pile cap, and when you calculate and when you actually tie up the reinforcement, it will start looking like a box of the steel bars, right? But it is necessary, and do not avoid any of the direction where you don't provide steel. So in all direction you should provide steel. The pile cap has to be designed either as a truss or beam theory, as we discussed. In case of beam theory, your bottom steel will be more, because we will be calculating area of steel in bottom based on the flexural performance of the pile cap itself. We will consider it as a beam supported on the support, simple supports, right? The pile cap are assumed to act as a simply supported beam, are designed for usual condition for the bending and shear. Their tendency is to fail by bursting, as I said, due to the high principal tension at the bottom, and therefore we require proper amount of steel in the bottom. The main reinforcement is usually bent, full bend, and extended up to the full depth of the pile cap. Here you can see, even this is not the proper way of doing it. You can see where the cursor is moving. This, once you have bent it, rich, you should see that this bent is reaching up to the top of the pile cap. Similarly, the top reinforcement should be extended up to the bottom of the pile cap. So these are the detailing requirements which you should take care while you are providing the design solution to the pile cap on the field. So the main reinforcement is usually bent and the extended up to the full depth, and check for the development length, which is very much necessary. A minimum reinforcement is 0.15% of dimensions, and main reinforcement as 0.12% of the dimensions in the secondary direction. For the busting force requirement, it is suggested that 25% of the main reinforcement shall be used. So suppose you have a main reinforcement of, let us say 100%, I mean 100 percentage, you can use additional 25% in the bottom to resist this busting horizontal forces. So they are actually the binders, horizontal binders, as you can see. They seem like this also, or you can use them in a vertical direction also, or a combination of both in the adequate locations. Adequate locations means necessarily on and above of the piles on the either direction. Suppose you have symmetrical location of the pile, like 4 piles, there is no option for you other than providing this lateral and vertical stirrups in the both the directions. So it will, that in that case it will acquire the shape of the box, right? Otherwise, when the area is sufficiently large for a pile cap, you can have, or you can avoid these kind of stirrups in respective directions. But otherwise, usually the pile caps are very small and block like structure. So all around you are providing reinforcements. So as such, please understand, here in this case, there is no case of changing the bar diameters frequently. So my advice will be like, whatever amount of steel you calculate, try to provide equal bar diameters in all directions. All directions means horizontal, vertical, top and bottom, right? So the main steel that you have to calculate based on the bending and other requirements, you should fulfill this requirement by equal diameters. And finally, here you can see, you should not, I would not advise you to carry on with this practice. Like you can see here that due to the more number of piles, we have provided steel in bottom only, and the top is not provided with the steel. That's not an advisable provision, because what happens is when the load concentration increases with the construction of the structure or superstructure, there are chances of getting or receiving cracks at this junction. So in that case, if you have not provided top steel in that case, there are chances of increasing number of the cracks around this junction. So always let us say minimum steel, but you should provide some top steel also. You can see there is a significant amount of depth over here for the pile cap, that is 700 mm. So uh, take this advice as your thumb rule for whenever you are designing any RCC element, that if your thickness of any of I say any of the RCC component crosses the limit of 400 mm, or let us say 300 mm ideally, then provide some minimum amount of steel on the opposite direction also. That means on the top and bottom, whatever is your opposite end, you should also provide some minimum amount of steel, because that much depth requires a lot of shrinkage to be handled. And if shrinkage is not properly handled, there are fear of the cracks always. So here in this case, you can see in the top figure where the cursor is moving, you can see it's a steel cage. So it's a pile cap itself, right? So this is a proper look of the pile cap, I would say, where you can see the bars are extended up to the top, bars are bent and going up to the bottom. And similarly, the bottom bars are bent and going up to the top. So that is in both direction, X and Y. So this is a very good provision of the steel to protect your pile from the busting forces also. So this is not a good option. Just I have mentioned this for your general understanding. So the arrangement of the reinforcement, let's have a quick look on that. The arrangement of the steel will depend on following parameters like load intensity and nature of loading, number of piles in a group, of course, the shape of the pile cap, the tendency of the piles to fail in the horizontal direction by bursting effects. You have to provide spatial steel for this, avoiding this bursting effect, and overall pile cap depth and dimensions. So how you will provide or how you will detail the reinforcement highly depends on these all parameters. As a practice, the steel reinforcement should be provided in all directions, as I said earlier. And additionally, the steel may be provided to reduce the stress concentration and to keep the cage of bars in shape while concreting. Suppose you have a, let us say, one column in this center of this pad, you should increase some top and let us say ideally the top reinforcement in addition to whatever the area of steel you have calculated to reduce the stress concentration, as I said earlier. Otherwise, you will start receiving the cracks at the junction in the top surface. And you know very well, as a behavior of the concrete, once there is a significant crack, you cannot then control it, not by retrofitting or by any method. You have to demolish it and reconcretize it. So that condition should be avoided in all possible cases. So now we'll have a quick look on the numerical. I will not be going through all the lines by lines, because ultimately you are going to receive this document, and where I insist that you please practice this with your own calculations, by hand calculations, at least once before you appear for the actual numerical in the exam. But definitely there are some typical steps. Now please understand, here I have just taken a solid example of the two piles in a group, and for that we are designing the pile cap. Designing of the pile cap more than two piles will require some sort of modification. Now this modification is always in terms of calculation of the bending moments, basically in X and Y direction. So according to the IS code provisions, we are designing this pile cap, right? So that thing you should keep in mind. So pile diameter, there are some data given to you, like pile diameter is 400 mm, spacing of the pile is also given, column dimension is provided. The factored load is also provided to you. The maximum moment is also given. Safe load on the pile is given to you, that is 500 kilonewton. In short, all the load data will be provided to you, and the spacing of the pile and pile diameter is also to be provided to you. Based on that, the first job that you have to obtain the dimension of your pile cap. So I would say pile pad, right? So this pile cap or pile pad dimension can be easily worked out with the help of this equation. Now this equation we already have seen in earlier discussion, so that you can directly adopt. That depends on the number of piles as well as pile spacing and pile diameter. So width and depth of the pile, that means lateral and longitudinal planar directions are provided in this step. So here we obtain it as 700 and 900 mm accordingly. So when you put everything in the form of a figure, here you can see on the one hand you have width of the pile cap, that is 700, and the depth of that means the lateral direction of the pile is the 800, and based on that you can design your complete pile cap, right? So this equation is from the IS code provisions: Pu upon N, Mu, Mx y upon sigma y square, Mx divided by sigma x square. So this is a combination of the moments. You may have come across earlier to this equation while you were designing the elements for combined stresses, direct and bending stresses, and especially when the moments are applied from both directions. So in our case, we have only one direction of the moment, so we'll take account of that direction only. Now there are some additional forces to be added, like self-weight of pile cap and factored load that you have obtained, and finally number of piles along the side of the axis, that is 2, right? This is x-axis, y-axis specified. So a moment that is given to us, that is 51.29. Now based on the loads on the pile, again you have to calculate the moment. So the compressive load in both the cases, like section 1 and 2, that you have to obtain accordingly, and using this equation it will give you the factored axial compression load. So this step is actually this one, right, where the data is used in a particular direction. So design working load you can obtain by dividing the factor of safety, and this has to be cross-checked with the safe load on a pile. Like on each pile, if you go back, safe load on the pile is 500 kilonewton. So this data is provided just to cross-check your own calculation. So here you can see that it's 400 kilonewton nearly, and the safe pile bearing capacity is 500 kilonewton. Now this data will be provided by the pile designers. So or the structural investigations has to be sufficed with the calculation prior to the design of the pile cap. So you have to obtain this data, right, before you start designing this pile cap. So naturally, the next steps, which are very straightforward and simple, bending moment has to be calculated. So right now, I'm taking moment of either of the forces, considering the forces in the center, and this much distance has to be considered as lever arm. So that is to be obtained by, let us say, half of this 800 mm minus the dimensions of this column as well as the pile diameter. So that will give you the total distance of the lever arm. So here exactly that is done over here. So you will get your moment which is acting on this section, and based on that you will be getting your depth requirement. So here you can see the depth is obtained by very well known equation 0.138 FCK BD square. So that will provide you the requirement of the depth of this pile cap. So effective depth and overall depth has to be calculated. Now you know how to do it, and cover and the half of the diameter and full of the diameter has to be subtracted for obtaining the D effective. So based on that, you calculate the effective depth of the pile cap. Then you go for the check of the one-way shear, and one-way shear has to be calculated based on the factored forces. And ultimately, you have to compare the actual stress and allowable stress. So now you know from the previous example also, or several examples you have gone through, like whenever you, this is not for pile cap only, whenever you want to cross check shear stress or one-way shear or two-way shear of any concrete element, I would say RCC element rather, two things to be done. One is you obtain the actual stress in the concrete based on the applied shear force and the area available at the section to resist that force, and the allowable shear stress according to the mixed design. So here, let us say it is, if it is given as M20, so the permissible value can be very well obtained based on that value. So then you have to compare the permissible and actual value of the stresses in the concrete. So punching shear and allowable shear are being compared here, which you will go through accordingly. You can understand that comparison also later on. However, it is safe, so should not be a problem because we have adopted good amount of thickness here. You can see this is 3044 is a periphery, and at the critical section, and 822 is the effective depth. We are not considering total depth, but we are just being on a conservative side. We are taking the effective depth only. This is the total force that is obtained. So actual shear stress at the location or desired cross section is 0.43, permissible is 1.12, so it's quite safe in that way. And then the calculation comes for the main reinforcement. So here the design aid can be utilized for obtaining the value of the amount of steel, and for that you have the all the values already calculated. Based on that, you have to obtain the constant values K and PT, percentage steel. Here there is an option, it's up to you. In the examination you will be allowed to use design aid also, or you can use that very well known equation, direct area of steel is equal to 50 into PT, right? You know that relationship very well. So it's up to you which equation you want to use for calculation of the area of steel. Now minimum steel and actual steel has to be considered. Here you can see the amount of the steel that is obtained from the actual data, that is 690, and based on that you can provide your area of steel in all direction. So 7 number of 12 mm bar diameter is in the top, and that is provided. So that provision should be provided in both ways, like X and Y, right? So the provided steel has to be larger than the requirement, so which is satisfying. So that is fine. And here again the check for the one-way shear at the face of the column again, that is to be adopted. So for that, based on the PT, percentage of steel, you have to carry out the check for the shear stress again at the face of the column. Earlier we have checked at the critical section where the column, I mean the pile was ending. So that was our critical section. Now you have to take it as the junction itself. So that is also quite satisfying. So you can go for a minimal reinforcement for the stirrups, 2 leg stirrups also. So this check will help you to obtain the spacing of the stirrups. That means that is indirectly in a form of the vertical reinforcement. So needless to add that this top and bottom steel is based on what we have calculated here in 6 step, and this cage like structure that you can see here is based on this stirrup design. So when stirrups takes the form of the vertical area of the steel, then you can provide top, bottom, and X and Y direction steel completely in your pile cap. So see, the method is very straightforward, but the point is you should at least go for manual calculation at once. I would suggest one more book for the pile cap design, that is titled as Reinforced Concrete Design by S.N. Sinha, and that's, I think, Tata McGraw-Hill publication that you can also use. There is a very good explanation of the design again given over here, but doesn't matter if you follow this pattern in the exam. That's quite fine for us. Like you can design, you can manage the design of the pile cap using these steps also. Friends, this is my general advice again to all of you, that whenever there is a question of design of any RCC member, ultimately you are looking for 3 points. One is the bending moment, right? Second is the amount of steel required, and third is the check for shear. So if you largely see to any of the I would say design aspect of any RCC member, this is for general discussion, any RCC member, when you are designing, ultimate goal is to do these 3 things, right? So it doesn't matter that which code you are following, which method you are adopting, which theoretical aspects you are considering. Ultimately, you have to design your RCC members for these 3 primary things. The dimension should be adequate, the amount of steel should be provided, and you should cross check the shear stress. So whether it is a foundation, then you have to go for 2 types of shear checks. Whether it is a RCC beam, ordinary beam, you have to go for ordinary shear check by means of shear stirrups. If you are designing columns, then you have to go for the horizontal thrust and the buckling requirements. So ultimately, only 3 jobs has to be done for any RCC design, right? So keeping these facts in mind, I hope if you practice with these numericals or similar numericals, you will be getting better confidence in your calculations, right? So I think it's done at our point. Uh, Pile cap design, you go through the practice example given over here when you receive this. And as I said earlier, 2 books are important. One is by Reynolds, Design of the Reinforced Concrete by Reynolds, and second is Reinforced Concrete Design by S.N. Sinha. Whichever book is, I would advise you not to use Reynolds book in exams, because it requires lot of minute calculations and may not be needed for exam point of view. But it is a good book for your practical, let us say, career. So avail that book and keep it in your library and use it in future. As far as exam is concerned, my material and the other books which I have suggested, like S.N. Sinha, will be sufficiently doing the job for your calculations. HJ Shah is also there. There are plenty number of books. Don't get confused. Whatever I supply to you, that will be more than sufficient for you to carry out the designs in the exams. So with this, I think we are done with all the most of the topics that we have in our syllabus. We started with the, I think, if I'm not wrong, we started with design of the slender columns. Then we went for corbels, dig beams. Then we went for the slab systems like flat slab and grid slabs. Then we also went for the types of foundations, which includes the raft foundation, combined foundation, and finally the pile cap foundation. So these many elements were necessary to discuss as a part of the syllabus, and I'm sure that based on this and also the counterpart, which deals with the design of the water retaining structure and silos and all. So I'm sure that by combining all the knowledge together, you will be in a better position to design any spatial structure. So you may have noticed that whatever discussion we did were regarding the spatial structures only. There was no ordinary design like simple slab and simple footing and simple column or beam was there. Everything was highly integrated approach. So always use wise decisions. Of course, the IS codes or any other international code is available, but ultimate decision has to be taken by the engineer only. That means you, right? So friends, with this statement of the conclusion that we have done a kind of sensibly large amount of the exercises, and we have gone through all the minimum required details in all the designs of all spatial structures. We end the sessions and we end the subject also ideally from my side. So in case if needed, I will be offering you some additional session in case if it is needed. Otherwise, this is fine from my side, and I'll be sharing materials again and again repeatedly as and when I come across that this is to be shared to you. I will definitely share with you. Rest assured about it. Don't worry about it. You are not going to run out of these sources anytime. So don't worry about any of the points, right? But you can reach to me. You can email me in case if you want any additional help. I'm always ready to give you the details. So with this, thank you all for joining this session. And I hope that you are maintaining good social distance and following the COVID guidelines in this pandemic again. So thank you all for joining the session. Have a good day.